What's the next speaker?
Okay, how's this for volume? Good? Yeah?
Yes.
Okay. Yeah, so my name is Paul Krogmeier. I'll tell you about this work on languages with decidable learning. This is work with my advisor Madhu at the University of Illinois. Right, so this work is about symbolic learning and synthesis from examples, and in particular, a generic algorithmic technique for getting decision procedures for these problems. So many applications of symbolic learning, well-studied problems like program synthesis, where you're trying to construct a program from examples to fill out your spreadsheets, or in verification, trying to find invariants for proving distributed protocols correct. These are naturally expressed in quantified logics, trying to synthesize tedious to write SQL queries from examples, and also in things like mathematics. There's been some interesting work trying to conjecture interesting theorems in graph theory in sort of example-driven synthesis loops. Some of my own work on trying to synthesize axiomatizations for classes of structures. And then also this morning there was a nice talk on synthesizing program specifications from examples. All right, so there's lots of applications, and this talk is going to try to tell you something about something that they all have in common when it comes to learning in these languages. So this is an algorithmic meta-theorem for symbolic learning problems that at a very high level says, if you can write a specific kind of interpreter for your symbolic language, then you can kind of compile that interpreter into an algorithm for the learning problem, the synthesis problem, that's actually a decision procedure. Okay, so in the remainder of the talk, when I talk about learning, I mean this generic concept learning problem. So you have some symbolic language L, and you're given two things: a grammar G over the expressions of L, and a finite set of examples. Okay? And then the goal is just to find an expression in the grammar that's consistent with the examples. So consistent depends on the problem. All right, so here's an example. So you've got these 4 graphs. The 2 on the left are labeled positive, the 2 on the right are labeled negative. And the goal is to find some logical formula phi that holds on the positive graphs and not on the negative graphs. So now if I told you that the grammar here, it's first order logic, but you only get to use conjunction and existential quantification. So no universal quantification, no disjunction, no negation. In that case, it turns out that there's no concept which can classify these, right? So in general, how do you decide that? How do you search an infinite space of expressions or programs and conclude that there's no solution? Yeah. So this doesn't just have to be about programming languages or classical logics. This is also about things like learning regular expressions. So you might have a set of positively, negatively labeled strings, like valid email addresses and invalid ones, and I say, give me a regular expression which matches the valid ones and not the invalid ones, right? So the question is, when can we find terminating algorithms? So these are expressive languages with infinitely many programs or formulas, so you can't naively enumerate them and still conclude that there's no solution when there isn't, right? Another point I want to emphasize is, if you're expressive enough, you can define examples up to isomorphism. And so we don't like that. I mean, learning regular expressions from these words, like A, B, A, B, A, B, A, B, A, B. We like A, B star, right? We don't like the one that says, oh, it's either positive example number 1, or number 2, or number 3. So that's A, B, plus A, B, A, B, plus A, B, A, B, A, B. So the grammar is crucial, and it also makes the problem computationally complex. Okay, so back to this meta-theorem. You come to me with a symbolic language L and you say, I want to do learning or synthesis from examples in L. So this meta-theorem says, okay, write a suitable interpreter and we can compile it to a learning algorithm that's actually a decision procedure. Okay. This interpreter has a particular form. It's a little recursive program and it takes 2 inputs, a structure, an example, and an expression. And it's going to compute either true or false depending on the problem. So if we're learning in first order logic, we'll write this little interpreter called FOL. That takes a graph, perhaps, and a first-order formula phi, and it computes true exactly when the graph satisfies phi. Or if we're learning regular expressions, we'll write an interpreter called reg that takes a word and a regular expression and computes true exactly when the word is matched by the regular expression in its language. So we have this programming language called Facet. It's sort of a notational tool for writing these interpreters, right? I'm not going to talk about the syntax and semantics. If you're interested, ask me after or see the paper for the formalization. The only thing I want to point out is that these programs in Facet take the expression. Remember, there's two inputs, structure and expression. They take the expression as a syntax tree, and the only way they access it is by referring to a pointer n that points into the syntax tree, and they can walk up and down on the tree by going to the parent or going to the child or the left child or the right child. And so they're kind of computing on the tree, updating a little bit of state as they go. So we'll see an example. Okay, now the Meta-theorem, specialized in light of this language Facet, says, given the language L, write a Facet interpreter for L, and then you'll get a learning algorithm. Okay. The crucial requirement here, so the interpreter has a requirement on the memory that it uses, right? It takes a structure and an expression, and it needs to compute the semantics of the language, basically. So it needs to store the structure and the expression somewhere, but how much memory does it use over and above those things? So that extra memory, which I'm putting in the middle there, should not depend much on the expression. It gets to point into the syntax tree using pointers, but that's it, okay? It can depend wildly on the structure, however much it wants, right? So it gets to use memory that as the structure grows, the memory can go up, but as the expression grows, it can't use any more memory for a fixed structure. Okay. The proof of the Meta-theorem kind of relies on translating these interpreters to tree automata. So in a learning problem, you get some examples, right? And you can say, I'm going to specialize the interpreter for each of these examples. And then that object you can translate to what's called a two-way alternating tree automaton. And then algorithms we can get by using tree automata emptiness checking. So you get these tree automata, you take a large product of them, and what you end up with is this final tree automaton whose language is exactly the solution set for the learning problem. Okay. So now I'm going to walk you through an example of learning regular expressions, right? So we want to learn them, we want an algorithm, so we're going to write this interpreter called reg, which takes a word W, a regular expression E, computes true if the word is matched by E, okay? The question you have to ask when using this Meta-theorem is, what kind of memory do I need to do the job? In the case of regular expressions, it turns out that you need to keep track of the subwords of the input word W, okay? So I'm going to represent a subword with just two indices into the word L and R, so L's on the left, R's on the right, okay? So now I've made that extra memory explicit as that middle parameter there, and the program on a word W with this LR and a regular expression that's pointed to by N, this program will compute true exactly when the subword from L to R in W is matched by the expression that I'm pointing at with N, okay? Here's the interpreter, right? It's fairly simple. So I'm just showing a few cases for like a subset of regular expressions. Let's suppose that we're working over the regular expression AB star, right? So initially the pointer is looking at the root, so it's seeing the Kleene star symbol. And initially L and R would be the first position of W and the last position, but that'll change as the program computes. So it's reading the star symbol and it says, this is really just intuitively what regular expression semantics is. You've got a word, you want to break it up into a prefix and a suffix, and check that the prefix matches the internal part of the expression that has the star around it, and then check that the suffix matches the starred regular expression again, right? So that's what's happening in this case. If L is equal to R, so if I'm checking the empty word, then I'll return true because the empty word is matched by any starred regular expression. Otherwise, I need to find if there's any way to productively decompose W by splitting it into a prefix and suffix and recursively calling the program either at the child node, the A concat B in this case, and also at the current expression to check the suffix of the word is matched. Okay. And then concatenation is just a simpler version of that, really, finding any split of the word and checking that the subregular expressions match the prefix and suffix. And then in the base case, if you're reading an alphabet symbol X, you just check the word I'm checking, the subword should be of length 1, and the letter that I'm actually looking at should be X. Okay. So if you believe that this is a correct interpreter of regular expressions, then our Meta-theorem gives you a decision procedure for learning regular expressions. Okay, so stepping back, what we have is these interpreters in a programming language for writing them, and a meta-theorem which takes the interpreters and compiles them to tree automata and gives you decision procedures for these learning problems, with the decision procedures being based on tree automata and emptiness. So now, which languages have we used this for to prove decidable learning and get algorithms? I'm going to talk about 2 of them, but in the paper there are 7 decidability results, and each of the interpreters is kind of interesting, so I'm happy to talk about them if you're curious. So here's one example. This is learning context-free grammars, given words as examples. So the problem is you have some labeled words, positive and negative, like regular expressions, but now you want to find a context-free grammar that generates the positive words and doesn't generate the negative words. Right? So what you need to do is you have to represent this grammar somehow as a tree, so like this on the right here. Many ways to do it, I've just sort of picked one. And then you're going to write this interpreter that walks up and down on this tree, parses the word, and checks that it's generated. So it turns out you can do that with an amount of memory that's bounded by the size of the word, but not the length, the number of productions, or the size of the terms in the productions. Right? And the memory that you need to do that roughly is subwords, a counter to handle recursion correctly, and then some extra bits of information to parse the word. Okay, this one is pretty cool. This is learning functional programs in the DSL from Sumit Gulwani's work on flash fill. So this is a DSL for writing programs that manipulate strings in spreadsheets, right? So you're wanting to move a string like international business machines to IBM, and you've got some looping programs. So this is actually decidable learning for a significant extension of his DSL. He had a restriction on the regular expressions, and there were no nested loops, and we can easily interpret those this way. And the memory roughly boils down to subwords, some bounded arithmetic, and finite maps. Okay, so here's the full list of results. We also looked at learning linear temporal logic formulas over infinite periodic words, learning propositional modal logic on Kripke structures, computation tree logic on Kripke structures, and learning in an infinite domain of first-order queries over rational numbers with order. And then the last 3 I've talked about: regular expressions, context-free grammars, and functional programs in the flash fill DSL. I also want to point out this work generalizes, and you can get these recent results that we had in POPL 2 years ago on learning in finite variable logics. Okay, future work. This is a kind of a theoretical thing that I think is potentially interesting. So there are these classic constructions from model checking where you take properties, like a linear temporal logic formula phi, and you can construct automata that read execution traces of systems or programs, and these automata check that the trace has a certain property. What we're doing is kind of going in the other direction. So these are constructions for learning that take arbitrary structures, like arbitrary graphs, and they build automata that read syntax trees of programs or formulas and say yes or no if the programs or formulas work on a structure. Right? So I'm wondering if there's some more formal connection that could be established here. Okay, the second one is, can we compile these interpreters to efficient learning algorithms? Right? So under the hood, these tree automata constructions are fairly complex. There's 2 directions that the scaling happens in. There's structures getting larger, right? And that's a problem. And there's also more and more examples, right? So how can we tame both of these to get efficient algorithms in some cases? I think there's a lot of hope and promise for this. I think the flash fill work, it's written in terms of version space algebra. It turns out VSAs are an instance of tree automata. So I think there are good proofs of concept that these kinds of algorithms can be made practical by carefully designing the language to not be too complex to search. All right, to conclude, I've talked about learning symbolic concepts from structured data. We have many decidable learning results. You can obtain many, many more by writing these interpreters. And this is also an algorithmic framework for learning, right? Algorithms based on tree automata and emptiness. Many applications, like I mentioned at the beginning, so now it's time to tame the complexity. That's all I had to say. So thanks to my advisor, Madhu, and to friends and colleagues for good discussions on this work. And here's my website. Happy to answer questions over email also. I'm also on the job market, so if you like this work, please get in touch. I'd be happy to talk more about it. Thanks.
I'd like to invite the audience to come up to the microphones to ask questions, if anyone has any. And please just introduce yourself for the online audience.
Sofia Drosopoulou, thank you. Very interesting talk. I was a bit surprised that at some point you said you can go down and up the tree, but I thought that the interpreters that you wrote were doing pattern matching and therefore were only going down the tree. How's that?
Good question. Yeah, I talked about the regular expression interpreter, and that one, it stayed at the same node and it went down, but you're right, it didn't go up. They can also go up. In the context-free grammar case, you have to go up and down arbitrarily.
I thought that your interpreter language would forbid you from going up the tree, the way that you have defined the interpreter language.
No, you can go up, yeah. Thank you.
Hi, Paul. Great talk. I'm Gautam from CU Boulder.
Thanks.
And great work as well. So I have a quick question about expressivity of the language that you have, right? So if I were to express a fully recursive functional language in your language, what is the blocker? Like, why can't I express? Because if I can express it, then the learning is decidable for a fully recursive functional language, right? But I'm assuming that's not the case. So what prevents me from writing a functional language in your...
Right, so these programs can be arbitrarily large, but the memory you need to evaluate them is bounded by these structures, examples. And all you need is that given fixed structures, inputs to a learning or synthesis problem, you can compute this amount of memory that you need, right? So if you imagined trying to interpret lambda calculus terms, you can't do that with bounded memory in any obvious way. I mean, you could fix the depth of the terms, you could do many things, but it would fail because you can't get a bound on how large the terms will get, and sort of they're kind of mixed together. The memory and the data and the program are kind of mixed there, and I don't know how to separate them. But
I see. Okay, thank you.
All right, let's thank the speaker again.